Okay, we are recording. We're all set to go.
Good. Well, good afternoon, everyone. Welcome to part 2 of my lecture series. So today we'll be talking about many examples in precision health in particular. And if we have the time, I'll talk about cautious view towards the future, basically the singularity, my point of view regarding the singularity and things like that. So we'll see how much we can cram in this 1 hour and 20 minutes. Otherwise, we'll continue it on Thursday. So last week, basically, I talked about what AI is, artificial intelligence, the fact that it started in the 50s, so it's not new. In the early days, they were trying to basically mimic human intelligence, believing that we can break down any cognitive activity that the human does into pieces, and we can program each piece alone and then put them all together and we can create an intelligent machine. That wasn't the case, and the hype kind of disappeared, but it came back again in the 80s thanks to different technologies like expert systems. But what is important to us here is machine learning. Machine learning also gave a new hope towards the 80s. And I define more or less what machine learning is. And recently, one technique within machine learning called deep learning has brought AI to the forefront again. So what you had to remember is the fact that machine learning is part of AI and deep learning is part of machine learning. They're not synonymous. And also we talked about the reasons why AI is coming back these days. So why this resurgence of AI? And I mentioned that there are mainly 3 factors that are powering the new rise of AI, namely the abundant data. We have a lot of data. Also, high performance computing. Computers are getting way better than what they used to be. And in addition, the development of new powerful algorithms. So today I'll be talking about applications, particularly in precision health. Let me close this. But before I do that, I wanted to remind you what is machine learning, and more precisely, what is actually supervised learning, supervised machine learning. So, and this is important because most of the applications that I'll be talking about actually hinge on this. This is the basis of all these applications. So basically what you have some data that is labeled, and here I'm representing the labels with colors. You have an algorithm that goes through that, understand the patterns in the data, and then generate what we call a classification model or predictive model. Then in parallel, you will have data that hasn't been seen before, so it's not labeled, and we will use this predictive model to predict their labels automatically. So the original labels here are done by a human expert. We learn from that, that's the experience, and then the predictive models, typically there's one, but you can have many, an ensemble of models. They will learn, well, they learned already, but they will be predicting the labels of unseen data. So the model can be deep learning, a neural network, for example, but they can be other things too. So let's see how we can use this in medicine, and more particularly in precision health. As we know, medicine is inherently personal, but currently we are treating the same different people with the same symptoms. If we give them the same treatment, this is the wrong way. Precision health is trying to basically divide this cohort into subgroups and give them the appropriate treatment, not the same for one shoe fits all, basically. So I would like to be able, even though they have the same symptoms, treat them differently based on their characteristics. And this is true for treatment, but also for diagnostic, prognostic, and other. Often people think that the way we do this is using genetics. This is how you can distinguish one individual from the other. That is true in some applications, but it's not always the case. So indeed, we use microarray data analysis, SNPs, for single nucleotide polymorphisms. These are the mutations in the genes, all the different genomics, metabolomics, microbiome, etc. But now precision health or personalized medicine encompasses more than just genetics. And I'll show you some examples. I'll start with examples with genomics, but I'll show you other examples that have absolutely nothing to do with any omics. So how is it done? So here I'm giving you an example with predicting the reoccurrence of cancer. So we have a patient, we want to know, we treated her and we want to know if she will have cancer again. So we have data about this patients. These are about the protein in between the cells. Doesn't really matter much, but basically I have a record and I need to predict whether the disease will reoccur or not. So the way it works is I'll use historical data. So data about other patients. I have their data. I have many, many of them. And I have this information whether for them the disease reoccurred or not. And using this historical data, I will build a classifier, which we represented by a cloud here. Now that I have this predictive model, I'll feed it the information about the new patient, and it will tell me whether the disease will reoccur or not. So you notice that here the schema of the data is the same. What is missing is this column here, basically what I knew about the other patients, and I want to predict it for this patient. And this is what this classifier will do. It'll say, oops, no, it will not recur, for example. So this same idea can be used in many applications. Here's an application for determining whether a patient is ER positive or negative. So this is for estrogen receptors. In the case of breast cancer, so we do a biopsy, microarray data analysis to see the expressions of the different genes. And this data for this particular patient and the past data of other patients for which we knew whether they were ER positive or negative, well, we'll learn a classifier, and that classifier will tell us if this particular patient is ER positive or negative. And this seems to be, well, according to these studies, and it has been published, it's actually more precise than the current technique of immunohistochemistry that is being used. Why do we need to know if a patient is ER positive or negative? Because we can then administer a different adjuvant treatment after chemotherapy for those who are ER positive or negative. So this is dividing the cohort into two subgroups and giving them a different treatment for the same symptoms because they have different characteristics. The same idea can be applied for many, many applications. So remember here, I used microarray data. I can also use SNPs, and it can be done to predict who will develop breast cancer, who will have a reoccurrence of the disease. In kidney transplant, you can predict who will reject a new organ, for example. In prostate cancer, you can predict the toxicity level. For cancer, you can predict loss of muscle mass, like decaxia. So this has been applied in many, many applications in medicine. Now I'll show you another example where I'm not using any SNPs or microarray data. Now this is the case of diabetic retinopathy grading. So retinopathy is a damage of the retina of the eye, typically in the blood vessels. So the diabetic retinopathy is the main cause of blindness in both developing countries, but also developed countries. It is due to the sharp sugar crystals in the blood that literally cut through the vessels in the retina. And as I said, it causes blindness. It's very common, but if we detect it early, we treat it early, it reduces the risk of severe vision loss by 98%. So it's very successful. The treatment is very successful if we do it early. So it's very important to detect that early. And we can't screen millions and millions of people. We need automated ways of doing this. And this is where machine learning can help. So grading is basically labeling these images into 4 different categories based on the microaneurysms and the hemorrhage that can be seen in the retinal images. So these are the intervals. It's not, anyways, I don't know exactly why they define these intervals, but these are the grades 0, 1, 2, 3. And we would like to identify the grade for each retinal image. So we build a classifier based on images that have been graded by experts. But grading alone is not enough. And what we can do is also, so we can take images like that and learn a model that can predict the grade. But the doctors would like to have more evidence. So what we can do is also take images that have been labeled on the pixel level. Unfortunately, this is very expensive to do. So we have very small data sets to do that. And we have a second model that learns the important parts of the image. And we combine these two, we call it knowledge transfer, to build a classifier that not only will grade the image, but also highlights the hotspots in the image. So a heat map, and it tells the, sorry, it tells the physician where is the regions of interest in the image, like here, for example. Can be done with metabolomics. Sorry, don't worry, I'm not sick. It's just I've been speaking the whole morning. This is the case of a spectroscopy of the NMR with a urine sample, and we can predict as well. We learn from past patients that have been labeled, and then we can then label a new case. And this is in the case of decaxia, to determine whether somebody is losing the muscle mass, yes or no. But it can also be used for all sorts of things, for diagnosis and prognosis. This is another example, completely different. This is the case of helping to determine the quantity of insulin to inject for people with diabetes type 1. So people who have diabetes type 1, basically they don't have insulin, they don't produce insulin anymore. And they have to inject themselves 3 times a day with insulin, sometimes even more, 4 times a day. And the way it works, the doctor tells them this is the amount of insulin you have to inject yourself every day, and then they have to write in a journal the amount of insulin they injected, and also the sugar level in their blood whenever they test, in addition to the activities that they do every day and whatever they eat. That's what they have to do every single day. And then once every 3 months, or sometimes even longer, 4 months, 6 months, they go to the doctor and they show the journal, and then the doctor will say, oh, okay, now you can increase the amount of insulin or reduce the amount of insulin. And then they come back again 3 months later, which doesn't make sense. So the idea is to learn a process to, we learn a policy to determine how much insulin they have to inject every single day. So it's not the same amount for 6 months, but every single day is different because we have different activities every day. We eat different things every day. So this is an adaptive system for each individual patient. Okay, I'm just going to skip this. Here's another example, again, completely different. By the way, the previous example is using reinforcement learning, not the typical supervised learning. But here's another example where we use supervised learning. This is the case of patients with the Workers' Compensation Board. They're injured at work, and they go to the Workers' Compensation Board clinic, and they are given a treatment. After the treatment, there's an assessment to see whether they should go back to work or they need another treatment. And if they need another treatment, which one? And then we give them that treatment, and there's yet another assessment and evaluation to see whether they should go back to work or we have another treatment. So it's an iteration. Unfortunately, if you look at most of the patients, we have many iterations like this. And that's a problem because we waste time. They're not back to normal. They're not back to work. And the companies or wherever they were working, they lose money. So what we were asked to do is to build a recommender system that, or a decision support system that looks at the evaluation and recommends what secondary treatment they should get. And we looked at cases where you have very long iterations and cases where you had very short iterations. And we learned from those a predictive model that allows an evaluator to see the recommendation of a system, a decision support system, and the reason why they recommend that particular treatment, and then make a decision. So as I said, we used the cases that were good, and we learned from them a predictive model, and a predictive model helped the assessors decide what treatment to take. Now, the data used here is simply questionnaires that the assessors were filling, asking questions to the patient. So these are just yes/no kind of questions. Has nothing to do with genes or SNPs or urine tests or whatever. Okay. And it was very successful. Another example, just to show you how broad this can be. This is an example that I particularly like because it shows how machine learning not only, machine learning is a way to build tools to help doctors. It's not to replace doctors, but to help them do the job better or faster or more accurately. So this is the case of a patient who needs brain surgery, and before the brain surgery, there is a segmentation that is done typically manually on the screen. You have to do a volume segmentation of what needs to be either cut or bombarded with X-ray, depending upon the treatment that they're having. I believe this one is in the case of surgery. Anyways, they have to do this volume segmentation. It's a very tedious job that the doctor has to do, and it takes between 20 to 30 minutes per patient. And interestingly, if you ask two doctors to do it, they may not give you exactly the same segmentation. Actually, the same doctor doing it in the morning or the afternoon may not give you the same exact segmentation. It's a very difficult task, and that's why it takes time. And the idea is to learn from the good segmentations a model that can predict what the segmentation should be for each patient. And so it's done automatically, but it's not to replace the doctor. It is to initialize the segmentation that the doctor will do. Rather than the doctor starting from scratch, from zero to do the segmentation, they start from something that the computer has done. And then the only thing they have to do is to adjust these borders, left or right or up or down. And instead of spending 20 to 30 minutes, they'll spend 5 minutes. So they save a lot of time. Here's another example, again, completely different. And I chose these on purpose to show you how different these applications can be. This is more related to mental health, the detection of depression from text. So we can detect emotions expressed in text. We can detect the emotions changing in time. These are the different emotions in time. And we published many papers regarding that. But now we can also detect signs of depression. We published that fairly recently. So we can detect from a written text or spoken text, spoken language that has been transformed into text. We can detect emotions, and we can detect signs of anxiety, depression. I wouldn't say diagnostic of depression, but more detection of signs of anxiety and depression. How do we do that? It's exactly the same thing. Again, we have text that has been labeled by experts saying this is a depression, this is not depression, or this is anger, this is disgust, this is fear, and so forth. And you learn from that to identify the patterns in the text, the language characteristics that are attached to each of these labels. And then the predictive model can be used for new text that hasn't been seen before and label it automatically. So that's about precision health very quickly. So machine learning is really key, is capital to develop these applications. And as I showed you in many examples, now the definition encompasses more than just genetics and all the other omics. And it can be anything, can be text, can be a questionnaire, yes, no, can be a urine test, it can be anyways, many different kind of data sources can be used. And AI will transform completely this field by building tools that we didn't even foresee in the past. Yeah, any questions here? Should I stop to set 2 minutes to see if there are questions?
No questions here.
No questions here. What about the chat? I don't see the chat.
There are no questions in the chat. Yeah. So it's absolutely clear.
Okay. Oh, I went too fast and nobody understood anything.
No, that's not true.
I hope everything was clear. So, but despite all these amazing applications, many people are still alarmed and worried about this machine learning and AI in medicine or other applications. Again, this idea of them, the machine against us, we don't have control over that. They will take over. There are other concerns regarding privacy, and I understand that. But we can have a long discussion about privacy, the meaning of privacy, the notion of privacy, the definition of privacy is changing with the new generation, especially with the use of social media. They'll show you how people very easily, we give up on privacy to get access to some benefits in business. So why not in health, where actually the danger is even, well, the danger is smaller. So if you go to e-business, often they talk about the DNA of the customer. Has nothing to do with the real DNA, but I'm representing it with the double helix here. So the DNA, they put information that they can collect about you. So suppose we have an e-commerce site. I will go there for the first time, I'll register. You have to register. You have to give some information voluntarily, your name, where you live, because they will send you the stuff at home. They may ask you for your profession, your telephone number, your age. I don't know why. Maybe to send you a postcard for your birthday. But anyways, this is the information that you think they know about you, and that's all they know about you, and you gave it to them. But then you start buying things. So you start activities, and what do? You purchase things. So for example, I purchased goggles, I purchased a watch for swimming. Oops, these two are swimming. So this guy is swimming. I never told them I swim, but just because I bought these things, they can infer that information. I buy helmets for bicycles. Oh, it's not just swimming. He does bicycles as well. So he's in athletics. I may give them some noise. Like I buy a coffee machine. I don't drink coffee machine, but I bought it, for example, I don't know, my friends got married and I bought that as a gift. So they think it's for me and they think I drink coffee, which is wrong. But most of the things that I'll buy will be correct. So that's my activity. But then I have also other behavior in the site. I do searches. For example, I search on home improvement and they know, oops, he owns a house, for example. I may review products, what I like and what I dislike. I reply to comments. If the site is selling books, for example, I start having friends. So what my friends like, we may have affinities. So basically, even if I don't express in my behavior and my activities that I like something, because my friends like it, maybe I also like it. So they start knowing more about me. Then they can also go to the web and search about me, search about my hobbies, my habits, where I work, where do I go. For example, they can go to Facebook and see my shares and who are my friends. They can go to Twitter and see what I tweet about and from where, so they can see where I am, where I went. They may check me on LinkedIn, where I worked, and who were my colleagues. Foursquare, I don't know, there's some sites like that teenagers, the young people use to tell their friends where they are, so they can identify me where I am. They can search on the search engines and identify the pictures and the videos that I upload or watch. Wikipedia, what I edited as entries, the news, the blogs. Oh, I showed you that with text, you can see signs of depression and emotions. Well, they can determine my emotions at different times. I forgot when I was angry last time, but they may know it. So they know more about me than my mother knows about me. And this is how they very accurately can target me with ads that I have a higher probability to act on and purchase. And we accept this because, well, it creeped on us little by little, but also because we know we get advantages. We get, I don't know, some points and discounts or whatever in some stores, and we accept that. But imagine if we were able to do this. This is scary, but this is happening. This is exactly what is happening today. But imagine if we can do that in medicine. So here I have my patient DNA, let's call it. It's not the customer DNA, but the patient DNA. And we have generic data like the gender, the name, the age, maybe ethnicity. Not in Canada, but in the US, they collect it. And then you have the electronic health record, electronic medical record history, basically. Well, it's not necessarily digital. It's still all on paper, but we're digitizing a big chunk of it. Then you add to the historic data, the generic data, other data. Well, the historic data, you have all the prescriptions, the drugs that you had in the past, the medical images, x-rays, and so forth, the lab results. So historical data, you have a lot of data already, but you have also stuff about genetics, all the microarray data, the SNPs, the microbiome, metabolomics, and so forth. You can add other sources. There are many things like the medical devices, the blood tests, the pressure. There are many new sensors that we have nowadays are very cheap. Also the activities like your watch, the smart watch, whenever you go and run, how many steps, when you're active, when you're not active, and maybe also again using the social media and the blogs and so forth to know about your emotions, mental health. Also the places you went. Now with the you certainly heard about the contact tracing that they can do in some countries. We failed completely here, but in some other countries are very efficient at tracing people. With that kind of information, you have an incredible picture of each patient. And like in e-business, you were targeting them with ads. Here we can treat them with the right treatment when they have a particular disease, rather than giving them the same treatment for everybody who has the same symptoms. We can give them a very specific treatment regardless of the other people in the cohort. Still no reactions, no questions? No. Okay. So that's about machine learning and AI in medicine. I want to go back to now achievements in general, not just in medicine. AI already had incredible achievements that date already back to 1997 when Deep Blue, a program by IBM, beat Garry Kasparov at the game of chess. That was a big turning point. People realized, oh my gosh, chess is the toughest game. How can a machine beat the best of the humans? But just before that, and it wasn't covered by the media as much as the Deep Blue match against Garry Kasparov, from the University of Alberta, we developed Chinook. I don't know if Jonathan Schaefer will talk in this class. No. So Jonathan Schaefer is a professor in computing science. He was also the dean of science until recently. He has this program, Chinook, that plays checkers. And Chinook beat Marion Tinsley, the world champion at checkers, but not, I mean, unlike Deep Blue, where they had this one match, Chinook beat Marion Tinsley in a world championship where you have different steps. And in 2007, actually, checkers was solved. So you cannot beat a computer. There's no way. The best thing you can do is a draw, because all the possibilities, all the different possible positions have been solved by the program. Other incredible achievements, also in the 90s, already self-driving cars were able to drive from Pittsburgh to San Diego. That was an incredible feat. And then DARPA had this competition. In the beginning, it was in an inhabited place, and then they build this urban kind of challenge, and different teams were competing to go from one place to another. So these are self-driving cars. Now we take it for granted. We have self-driving cars, not in Alberta, but in many places in the world, they have cars without drivers. That's all driven by machine learning and AI. One interesting achievement that Dr. Solis likes particularly is when Watson beat the best humans at the game of Jeopardy. That was in 2011. For those who haven't seen it, it was actually quite interesting and shocking for some people, but I'll tell you a little bit about the behind the scene. Another achievement, very recent, also related to the University of Alberta, the fact that now we can beat professional poker players, and in 2014, actually, the heads-up limit Texas Hold'em was solved as well. Let me see so in the history of AI, we had many ups and downs. Each time you have an incredible achievement, you have this peak of enthusiasm and interest in AI, and then it dwindles down a little bit until you have another achievement. So very recently, we had a big achievement when AlphaGo beat the best at Go, KG, and then we have many other peaks afterwards that may not be as covered by the media as the achievement of AlphaGo, but we will continue to do that. And you can see there is still a huge enthusiasm in AI. So it'll continue to go down, it cools down, and then we have another achievement, and it continues like that in an infinite iteration. Also recently, this is another thing that was covered in the media. That was last year. The paper came out in November 2020, but it was highly covered in February of 2021. Probably you didn't hear about it, but it could have an incredible impact, is the fact that computers are able to influence humans. So this we call adversarial vulnerability of human decision-making. There's a computer program, AI computer program, that is able to influence humans in their own decision. So they demonstrated it with 3 experiments that are covered in this paper. Of course, this kind of experiment fuels a lot of fear, and it goes back to the different warnings that we got from different personalities like Stephen Hawking, who pointed the finger at AI, saying this is an existential threat. Actually, artificial intelligence could spell the end of the human race, he said. He retracted a little bit on that, but many others followed suit, like Elon Musk, like Bill Gates, and others. Yeah, I'm going to skip this story about capitalism and the BBC, but you can read about it. Okay, so AI is not the only threat, obviously. There is also the nuclear war, there are biological accidents, and so forth. So let's go back to this AlphaGo. I mentioned AlphaGo. Some people didn't know about it when I mentioned it also in the first lecture. Go is, you can see here the board. It's a board game for 2 players, and they have 2 colors, black and white. These are small stones. And the goal is to cover as much area as possible in your color, and you conquer other areas of the black if you you build around them, so you encircle them. It's a very simple game, but there's so many possibilities. The search space is so large that for computers, it used to be very, very, very difficult to play against humans. Even though, as I said, we beat Garry Kasparov in '97 at chess and checkers. We beat Tinsley since 1994. The game Go was still very hard, and even kids were able to beat the best computers. So that we have a specialist in our computing science department at the University of Alberta, Martin Müller, who's a master at Go, and he was working on devising new computer programs to play Go, until a student came, an Australian student, David Silver, came to do a PhD here with Martin Müller and Rich Sutton. I mentioned Rich Sutton before. Rich Sutton is a specialist in reinforcement learning. And David Silver wanted to use reinforcement learning in addition to the heuristic search and planning that Martin Müller was using in Go. Combining these two, he wanted to build another new program. And that's what his PhD was about. And he succeeded to build a very, very strong player, actually. And then was hired by a small startup company in London, in the UK, And they asked him, oh, continue the work of your PhD. Here, we will give you resources and a team. And what can you do with that? And that's when he built the AlphaGo. He was the lead researcher on the AlphaGo. And they tried it on now champions. Well, I'll get back to that. So this small DeepMind startup was acquired by Google and at the end of 2013. So beginning of 2014 became public, and in a TED Talk show, Larry Page, one of the founders of Google, confided in the public that the reason why Google bought DeepMind, it's actually the fact that they have this program, a particular program that can play many Nintendo games. The same program can play different games and beat the humans. So this is interesting because most of the programs that are in AI, they're very specialized. Like you have a program that plays chess and beats Garry Kasparov, but that same program cannot do anything else but playing chess. Same thing, Chinook can only play checkers. It cannot be used for something else. Well, here you have one program that can play different games and beat the humans at all these games. And the interesting thing is that the people who are working on this game at DeepMind were also students from U of A, students of Michael Bowling in particular, who has the arcade learning environment program here at U of A. And they were also hired, as I said, by DeepMind. So DeepMind had this AlphaGo and this program, and that's one of the reasons why Google was interested in that. So with Google giving them more resources, they were able now to go and challenge humans. So they challenged Lee Sedol, 8-time world champion at Go, and surprise, surprise, they beat him. And that was a shock in the world. 8 times world champion, that's a big deal. But the Chinese were not very excited by that. They said, the world champion right now is from China and you cannot beat him. That's KG. So the team from AlphaGo, DeepMind, they said, okay, we'll challenge KG. And surprise, surprise, they beat him as well. So they went from not being able to even compete with a child to beating the best of the world. That was a shock. And how did they do that? Well, basically, they learned on past games. They're all recorded somewhere. But after doing this, they said, okay, what can we do better? Then they erased all these past games, said, why don't we actually teach it to play, and giving it just the rules of the game and let the program play against itself. So AlphaGo 0, this is the new version now. AlphaGo 0 means it doesn't see old games. It only has the rules of the games and it plays against itself. AlphaGo 0, after hours and hours of playing against itself, it was able to beat the original AlphaGo that beat the humans. That was another shock. That was in 2017. That's one of the huge peaks. I showed you this graph of the peaks whenever there's an incredible achievement and a huge hype around it. That's exactly what happened here. But again, it didn't stop there because since AlphaGo 0 was able to learn from the rules, learn to play against itself and learn the game, they said, why don't we give it the rules of chess instead of Go? And in few hours, AlphaGo 0 with chess was able to beat the best, not the best human, because that Garry Kasparov was crushed in 1997, but it was able to beat the best program of chess, 0 to 100 games. That's just in few, this is in October 2017, and now here's December 2017, so in 2 months. And then didn't stop there. because they took AlphaGo and they created AlphaStar to play other games. This is StarCraft, and their new program, AlphaStar, was able to beat professionals as well. So basically, the progress was incredible, and this is in January 2019, so almost a year later. So we're doing it. The progress is so fast. People are saying, there you go, the computers will replace us. But remember, these are very specialized kind of games. Yes, it's the same basic idea, you give it rules and it learns against itself, but you can't use this for driving a car, for knitting, for creating poetry, for everything else. Like, the humans are extremely, extremely versatile. These machines are not yet. So we achieved incredible feat, Jeopardy, AlphaGo, but do you think a computer can pass a university entrance exam, for example? Will it be able to do that in 2025? Any reactions? Do you think a computer could pass a bar exam to become a lawyer by 2030? Well, they can already. We have a program done here at U of A that can pass the bar exam in Japan in Japanese without knowing how to speak Japanese. And actually the students who worked on it, the graduate students who worked on it, don't speak Japanese either. So let me open this mysterious box like Watson and see how they are able to beat humans at a game like Jeopardy. Once you know the secret inside, it's not as fascinating. Like when you look at the magician, how they get the bunny out of the hat, it's impressive. But once you know the trick, it's not impressive anymore. So here's the game of Jeopardy. You get a question. Well, it's not a question. It's typically a statement. The answer has to be a question. The statement is Mozart's Last Symphony shares its name with this planet. And you have to say something about, a question that gives the answer to this planet. You'll see the idea if you haven't seen Jeopardy before. So Jeopardy generates a factoid kind of, well, the participants, they have to give as an answer a factoid question. Okay, so what the program does, it takes this statement, Mozart's Last Symphony shares its name with this planet, and extracts entities, we call them entities in natural language processing. So important entities from this sentence, for example, Mozart, Last Symphony. And then it generates a query out of these. So it takes these words and generates a query to a search engine. So for example, if I send it, and I'm simulating what it does, but I'm sending this to Google, Mozart Last Symphony, then I will get a bunch of these documents, okay? Then I'll go and take one of them, Symphony number 41, Mozart. This is in Wikipedia. I'll open it, and inside here, I will look for those words. So symphony, Mozart, symphony, and I'm looking for I have Last Symphony. And then in addition to that, I'm looking for words that are related to planets. So I'll go to the planets and I'll see I have Mercury, Venus, Earth, Mars, and so forth. And I will look for these words in this document. Oops, okay. And you can see the work is nicknamed the Jupiter Symphony. So the Last Symphony is the Jupiter Symphony. So the question is, what is Jupiter? Okay. So this is how it works. There's no very fancy smarts in there. It's almost algorithmic. But when you see it from outside the box, it's very impressive because it happens very, very fast. Now, can we do this? This is a factoid kind of question, but we can do the same thing for questions like true, false, did Charlemagne repel the Magyars? Is it true or is it false? How you do that? So you can search different sources like Wikipedia, and you can find different probabilities for the Avars, the Magyars, the Franks, and so forth. And then you can say, no, actually, there's a higher probability that Charlemagne repelled the Avars, not the Magyars, and then you say false. So with these techniques, you can answer multiple choice questions very easily and pass the bar exam to become a lawyer. Yeah, so going back to this fear of AI, that AI will become an existential threat for us. Is it serious? Of course it's serious, and many prominent people are talking about it. We should not dismiss it. And there are many institutes actually with serious people discussing it and thinking about the ethics of should we put limitations, or how do we control this? But having a fear to the point where we should stop everything is a mistake, because first of all, we're still far away from this machine that can replace us, but also what we are building tools that can help us do the things we're doing better. I'm going to skip this about how dumb computers can be. So is it really a possibility of paranoia? I think both is true. There is a paranoia right now, but there's also a possibility in a not so far future. But today, we're not there yet. And I showed you the example of even in computer vision, recognizing what a muffin is and what a chihuahua. I showed you many other examples. We are getting better and better, but we're still not at the level of the humans. Even though for some applications, the computers can beat the humans, but they do that without understanding. Like, for example, it was demonstrated many times already with some sophisticated deep learning architectures. We can build systems that can recognize melanoma on the skin, skin cancer, better than the humans. But the humans understand. The computers do not. And the computers cannot also explain the why. This led to a new field in AI called explainable AI, or XAI. The very good models that have very high accuracy are black boxes, and they can't explain their decision, why they predicted this or that. Why do they recommend this treatment and not the other treatment? We're still far from what humans are capable of. Yeah, so this warning about AI is not new. In the early days of AI, when the hype was at the maximum, they were already saying that we should be careful. It would be well if a large number of intelligent humans devote a lot of thought to these problems before they arise. This is Solomonov in 1967, one of the pioneers in AI. And he said that from the early days of AI. So it's not new. But especially with the new achievements, it's becoming clear that we are getting closer and closer, even though I insist again, we are not there yet. So we should devote considerable thought to this issue. We should not dismiss it, but it shouldn't stop us from continuing to do what we're doing right now. Just have to be careful. So this leads me to this idea of singularity. I don't know if you had the chance already to talk about it in class, but in the past we had many sessions on the singularity. So the singularity is this moment when basically computers will become as smart, if not smarter than humans. And when that happens, they will drive innovation, not humans anymore. And they will self-improve themselves. With this self-improvement, there will be an acceleration that we cannot understand. Actually, it'll be so fast. And this is why we call it the singularity. It's a fast rate of change that we will not comprehend, and therefore we cannot predict what will happen. Is it science fiction? Well, theoretically, it is possible. Is it? Can we have machines that are more intelligent than humans? Or are humans the maximum intelligence that can exist? Well, I'm using this analogy of a mouse. I showed you an example in the beginning of class of a dog, a very smart dog, or crow, or even ants. Well, let's take something in the middle, like a mouse. A mouse can cross the river, can swim. It's not a fish, but it can decide to cross the river if the food is on the other side. So it's adapting to its situation. It makes a decision. Well, cheese is not something that exists in nature. Humans created cheese, and mice apparently love it. They adapt to something new in their environment. When they build their nests, they will build their nests with whatever exists in their environments. If they're in the field, they will use what's in there. If they're in my garage, they will use the cables, the cardboard, the paper, whatever, the plastic. So they adapt. And adaptation is a sign of intelligence. When you put a mouse in a maze, they find their way to the targets, but when you put them again in that maze, they will do it faster because they memorize the maze and they know where to go. And retaining information is also a sign of intelligence. Actually, it was demonstrated that mice can count, can do arithmetic operations. 1 + 1 = 2, 3 - 1 is 2, but even more sophisticated than that, obviously. But can you imagine the mouse gazing at the stars and thinking about other planets with mice? Maybe not. Can you imagine the mouse looking at the cheese and imagining the protein structure of that makes up the cheese? Probably not. When the mouse comes to my garage to build its nest and it ends up being in the engine of my car because it's warm, it doesn't know what that engine is for. That's why it's nesting there. And I had a nest of actually squirrel, not a mouse, but close enough. It's if the mouse is in Florida watching a rocket blasting, it doesn't understand, doesn't comprehend that that's going to space. And it certainly cannot do mathematical abstractions, even though it can do arithmetic operations. So we are certainly superior because we can do all these activities the mouse cannot. And that means that we have different levels of intelligence. Suppose we are 0, we are intelligent, the human. The mouse is sub-intelligent. What that means is this could be something in the positive side. If we are at the level 0 and we have sub-intelligent, we can have super-intelligent. So what is a super-intelligent? It can be a computer, it can be a combination with biology and mechanics, whatever. But this hypothetical machine or thing that is more intelligent than us is definitely possible. And like the mouse can't imagine what we think. It only knows that we are a predator and we can kill it, but we can't conceivably think that the mouse could comprehend our degree of intelligence. It knows that we are superior, that's all. And it's the same way, we can imagine that this machine, hypothetical machine, could be more intelligent than us, but we can't comprehend the degree of that intelligence. What does that mean? Okay, so there are different ways of reaching this hypothetical machine. I call them the paths to the singularity, technological singularity. The first one is to help biology to improve with selection, and we create, and see, believe me, people have tried creating more intelligent people. This is completely unethical. And if we don't do it, then it'll take a very, 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 very long time to reach that goal. Because I can argue that Aristotle and Einstein have the same kind of level of intelligence, even though they're centuries apart. The second path to the singularity is if we improve artificial intelligence, which we are talking about, an artificial intelligence that will exceed the human intelligence and basically build a machine. But even though hardware is improving very rapidly, and I talked about it last time, software is lagging behind when we're not there yet. So it will also take a long time, and I don't believe it is the most secure way to get to that destination. The third path to technology, even though the number two, we can still do it, but I think it'll take longer. What can be faster, and people are working on this, this is what we call the Cybernetics Singularity, is the creation of human-computer interfaces so that biology and mechanics and electronics can combine and work together. And I'll zoom in a little bit more on this. This is what we call the Transhumanism Movement. How do you enhance the human body with electronics and machines, basically, to become better? Because the current human body is limited. The fourth path, something that very few people talk about, is some kind of intelligence, and not necessarily the intelligence that we know about. And even I mentioned last time that even in psychology, they're talking about different kinds of intelligence. There could be another intelligence that could emerge from a network of computers. This is like the example of the bridge that I showed you last time, the bridge formed by the ants. One single ant cannot make that decision. As the collective put together, they can, well, some kind of intelligence manifests itself through the collective and the cooperation between these ants or these insects or whatever. And we have that kind of thing with Internet of Things. There are small, smart objects, whether it's a thermostat or a car or a computer or something, or light bulb or something else, that are interconnected. Individually, they're not that smart, but put together, an intelligence could emerge from that. I say could. There's no proof of that, but something can happen, especially when they're also connected to smart computers. And one thing like that can be seen in nature, and I mentioned the ants. I have here a video, but I will not show it. You can go to YouTube and you can find it there. These are researchers who poured concrete in a big ant's nest, and they let it set, and then they dug through to identify the different chambers. And it's actually fascinating, the architecture of these nests, the different chambers that have different functions for the mushrooms, for other insects, and for, storage of food and storage of larvae and so forth. The kilometers of paths that connect them all. You cannot imagine that one ant has designed this whole thing or thought about it. It's the collective together came up with this fascinating architecture. So this being said, let's focus on the cybernetic singularity, because it has to do also with AI. We will have, there's no question about it, we will have a population of cyborgs. So cyborgs are people who are a mixture of humans and machines. And don't think about the humans adding mechanical things like, and we already have it. We have cyborgs already, like with prosthetics. So they're already among us. So don't only think about a human adding a mechanical electronic device. There's also the possibility of having robots to which we add biological cells. And this has happened already. There are, so one example that I like very much, and I talk about it often, is this robot rat. It's a robot that is controlled by few cells of a rat brain. And the interesting thing is they have many of them. So the rat brain is not on the computer, on the robot itself. It's on a Petri dish connected to a computer and remotely controlling this to move forward, backwards, and left and right. The interesting thing is that the brain cells die, and then they have to replace them, and they notice that the behavior is not necessarily the same. So even though the robots, like cookie cutters, they're designed the same way, because the brain cells are different, each one of these robots is completely behaves differently and learns differently. So you can have cyborgs by adding mechanics to or electronics to a human body, or you can have also a machine to which you add biological cells. And maybe one day we'll reach the $6 million man or the bionic woman. We're getting there. So I'll show you an example and why we will have a population of cyborgs. You all know what this is. This is a cochlear implant. It was invented more than a century ago. This is for people who cannot hear. So you create electrically, you simulate basically the nerves inside the inner ear to believe that they hear sound, even though the ear itself doesn't hear. And you see, it's actually quite common nowadays. But this is for hearing. Now we have these new devices that allow blind people to see. And this is an example of a retinal implant. There's a matrix here. You can see it. There's a picture of the matrix here. This is from a company in the US called Second Sight. But there are other companies that do it in Australia and Switzerland and London, UK. So there's a matrix that is implanted on the retina. And basically the patient, the blind person, is wearing these glasses, and the glasses have a camera on them. The camera signal is processed by a computer here, and the computer sends, with this antenna, sends the signal to this chip that is on this matrix that is implanted on the retina. And like the cochlear implant, it stimulates the neurons here and the optical nerve to believe it sees some flashes of light. And with that, you can create an image. So here's an example. This is with the this is of the University of Los Angeles, University of California, LA. This is an example where you see a picture, see this teddy bear with some bars here. You can see the shape, so it's not very good. But for letters, it's impressive. They have only 60 electrodes, so it's not much, but it's enough for a blind person to be able to read and see some signs. Actually, what they see is blurry black and white, and they see shapes, light, and movement, which is better than just black, nothing. Here's another example from a company in Australia. You can see this face, and they have more than 60. I don't know exactly how many electrodes they have here. Now they go beyond. Instead of having the implant on the retina, they go directly to the visual cortex. So they just implant the electrode on the, it's actually also a matrix on the visual cortex. So they bypass the eye completely. It's again a camera. You can see it here. There's the camera here and the computer and the antenna communicates with the receiver on the back of the skull. The images, as you see here, are not fantastic, but it's not bad. But they remind us the early digital cameras. So this is a 4x4, then a 16x16, and then soon, well, they don't have this yet. This is a simulation, 32x32, so 1024 pixels. I mean, from blindness to this kind of shape, that's impressive. But what will happen soon, we will be able to have more sophisticated cameras here that send more sophisticated signals to this one that transmits these signals to the receiver. For example, cameras that can see at night in the dark. So a blind person will be able to see in the dark. I cannot see in the dark. More than that, if this resolution of the matrix here gets better and better, well, let me show you a picture. We will be able to see like this. So you see this picture. This is a picture from a very special camera. This was taken more than 10 years ago in June of 2011 in Vancouver. What is interesting here is that people are in the crowd in downtown Vancouver, and you think they're hidden in the crowd. So each person is completely hidden in the crowd. This is a picture taken by a camera installed by the police. They didn't inform anybody. This was before the Stanley Cup finals in June of 2011. And not everybody could get in the stadium. The Canucks were playing, so everybody wanted to see. So CBC installed cameras outside, and the police predicted that in case the Canucks lose, there will be a big problem. And indeed, that's what happened. So they use these cameras to identify the culprits. And I'll show you what does it mean to have a camera like this. And one day it'll be in the eye of some people. And why only the blind people? Maybe normal people would like to have also that. Here's an example. Do you see that person standing next to that tree? Well, what person? There are many of them. Well, you can zoom in, okay? I'll zoom in right there. And this is what I can see. Do you see that person? He's suspicious. Well, you don't see him yet. He's somewhere here. I'll zoom in even further. Zoom in even further. So you can't hide. This is the picture, original picture. Now I can see the face. I can recognize the person. I cannot do that with the normal eye. This is what you have with current cameras. If I zoom in with a current camera, this is what I'll see. But this is with a sophisticated camera, I can see the details. You won't be able to do that unless you have a bionic eye. So people will start choosing to become cyborgs. I'll show you another example here. Oops, that's not what I wanted, sorry. I'll go back here. Another example, this is in Shanghai. Let's look at the zoom. Incredible zoom. And if somebody tells you, hey, I can give you an eye that can do that, would you choose to have a new eye? I'll show you on something else. I'll go back to that picture of so this is Tokyo. Imagine seeing from above the roof of a high building, you can see the city like this, and you want to see who's walking there in the street. Well, with a bionic eye, you could. Nothing is here, yeah. I can even see that there is garbage. You see there's garbage there. Well, with your eye today, nature didn't give you this capability. And if somebody tells you, hey, I'll give you that capability with a bionic eye, will you choose that? That's the question. And I can tell you many people will. And many people have started already doing that. Here's an example, people injecting an RFID in their skin. This is the size of a grain of rice, and the RFID uniquely identifies you, so they can open their car, they can open their house. Some companies now offer this to their employees. They can use them for to get food in the machines, distributors. It's actually relatively cheap to do, and many people are doing it. These are crazy young people who are installing LED lights underneath their skin that light up when they come close to a hotspot, a Wi-Fi hotspot. So they know where the hotspots are in the city. There's no regulation, so people can do whatever they want. And this guy, for example, installed a hard drive. I hope it's an SSD hard drive, a hard drive underneath his skin, and you can see that this is done at home in order to record from his camera that he's wearing on his shirt, record everything he watches. There's all sorts of things that people are adding. These are less intrusive. These are printed sensors that wash away after a while, but they can use them for sensing different things. They're called biostamps. Yeah, I think, what time is it now? Oh, I'm going to stop here to give you the chance to talk about what we saw today. I hope you're not shocked. We may have people like that circulating on campus, so open your eyes and check. Anyways, I'll stop here.
Okay, any questions?
I'll stop the sharing. Where do I stop sharing? Stop sharing here. Yeah.
Now we can see the people. So I'd like at least one question from this room. Okay, any questions from the Zoom people?
I can, and the chat has nothing.
Yeah, there. Yeah.
Oh.
Hi.
Hi.
Can you hear me? Hello.
Yes.
Yep.
This is just a theoretical question, because I guess we're in that kind of class. If we could create, because I know like in the middle of your lecture, you were saying that we haven't reached it yet, but maybe in the future sometime, the singularity. Oh no.
That's the singularity.
Sorry, that was my cat. So like if we do reach it,
Yes.
and like machines do surpass us in that sense,
We will.
Yeah, we will. I'm guessing that means that a lot of like the daily functions, such as like going to work or like jobs, farm work, all that kind of stuff might be taken over, ? Who knows? But like basically the economic structure that we have today will not be the same. What do you think, like what kind of economic structure? This is we're just talking.
No, these are very good questions.
Okay. What kind of economic structure would you like think would take over? That's just a question.
I'm not in economics, but I can speculate.
Speculate.
So already many of the mundane tasks, the boring tasks, can be done by computers and machines. And people are screaming, hey, we're losing our jobs, we're against that. Remember the first time they introduced robots in manufacturing, it was a big deal. Now all manufacturers of cars, for example, car manufacturers, they use robots and nobody talks about them anymore because we found jobs for people to do other things. And more jobs will be replaced by computers, even truck drivers. Soon we will have self-driving trucks, and why do we have to put a human there in the truck? Well, we will have to find another job for these people. And we are very inventive at creating other jobs that are more sophisticated and not boring. But eventually, all the jobs will be feasible by computers. So what do? So some people are talking about having computers, or the owner of the robots will have to pay taxes. So each robot will pay tax. because otherwise you have the rich people who can afford the robots. They will get richer and richer, and those who can't afford robots, what do? They die for hunger, and that will generate another, will provoke another revolution. So we need to think about it ahead of time, and one of the solutions is to tax the robots. The other solution is to have this the income for, guaranteed income to everybody. These people can then live with that guaranteed income, or add other jobs and other income. Or you can have holidays for life, or you can start reading and learning for life, or doing arts for life, or whatever, and you don't have to worry about food and shelter. And there are many ways of thinking about this. Again, I'm not an economist. But the humans are very inventive, and they will find a solution. And that should not stop us from having computers that can replace our dumb, repetitive kind of jobs.
Thank you. That's a good answer. Very nice. Yeah, I guess I was thinking about, like, I hope that the people of the future do not fight against this in a way that, like, leads to, as you said, like a separation of rich people and poor people, and then suffering. I really hope so.
People will always fight.
Yeah.
People fight for the masks and for the vaccines, so let alone their jobs and their, the perception of their livelihood and stuff like that. So there will be resistance for sure. So it'll take time. But like the Borgs say, resistance is futile.
Okay, thank you.
Yeah. Other questions?
There's a question from Sean as well afterwards.
I had a question. So when humans per se, we make technology, usually the objective is to in some way improve our lives and make our lives easier, right?
Yep.
So when we reach a singularity, what would be the function, or what would be the purpose of computer innovation? Like, computers who are more intelligent than us, what are they innovating for? What would be their focus? Because they don't have any biological functions, unless it's like securing electricity.
No, this is again also a very good question, and nobody really has an answer, because we can't comprehend what more intelligence will think and do, and even what is ethical and non-ethical for a more intelligent being. So we would think that it will continue to improve our conditions, our life. But if it becomes self-conscious about itself, maybe it will think about improving its own world and condition and life. And if we are in the way, that's the threat that people are talking about.
And then also in the same sense, if they don't self-actualize, right? And then they are more intelligent than us, but they don't have a function or like a purpose for innovating, then like who's to say they would even innovate? Like they don't have any reason to innovate, right?
Well, humans, the people who think, they are thinking about their purpose in life. But the majority of people don't even think about their purpose in life. I can guarantee you that a machine, an intelligent machine, will start thinking about its own purpose. And I don't know the answer that it will find. And I hope that it will find that our existence is necessary, and will live harmoniously with this new intelligent machine. I'm confident that that will happen.
What I think we should avoid is the idea that we're just asking what will happen. The reason you took this course is you can actually shape what happens. You
That's
can
good.
think about
That's good answer.
what would be desirable and you know, move us toward that direction. That's the reason for taking the course.
And
So
I
sim-
think, yeah,
Yeah.
no, that's a very good point.
Yeah.
But the reason also I insisted on the third path, what I call the third path, it's because I don't believe we will have machines and humans and this image of them against us. And this is how your questions were as well. I believe that humans and machines will be one, will be mixed.
Yeah, like our children. Rich Sutton is talking to you a week from today, next Tuesday. And what he says is smarter than human machines are like our children. And we can be proud of them, right? If you have biological children who are more capable than you, it's a good thing, right? And you know, you can do things socially together. And there's no reason that that would not be true with these offspring. Yeah, so that's.
But it brings up very interesting questions, however, because currently we can think of a prosthetic for somebody losing a limb in an accident at war or something like that. And even our social insurance will cover for it. So our society is covering for the expense to put a prosthetic. That's because there was an accident or a disease or something like that. But now we're coming to the point where people will choose. I don't want this arm. I want an arm that can pull heavier things and can turn 360 degrees and can be faster and whatever. I choose to cut my arm. Then should we pay for it? Should we allow it? And if we don't pay for it, then only the people who have the means will have that, and those who don't have the means don't have it. So it brings up all sorts of issues that we have to think about.
There are already societies that don't use money. I visited one of them about 15 years ago. It's called Oroville in India. And it's a very interesting place. They haven't used money for a long time. Shortly after I left, they had a brutal murder there. So obviously it doesn't solve everything. But if you think about it, there are a lot of things in your life that seem real to you that are really fantasies, that are completely fictional. And money is one of them, right? Money isn't like a real thing. And we're just used to these fictions. But eventually it won't be useful to have that particular fiction, and we won't be using money anymore. Why? Because in a post-scarcity world, the price of valuable things will come down to practically zero. And when you wake up in the morning, unlike today, when you wake up in the morning today, you're thinking of all these regrets, things you want, you can never have, things you want to do, you can never do. But in the future, neither one would be true. Virtual reality would be better than real, shareable with friends, and the price of valuable things comes down to practically zero. Yeah, so you should not think that the life you know today is always going to be the same, right? All these things will change. Yeah.
Cool.
Other questions?
Sean had a question at one point.
Yeah, Sean.
Then I have to go.
Right.
So my question, so in semiotics, we understand human sign systems. So for example, numbers and language are sign systems. My question is, we as humans generate unique sign systems. You know, we invent new words or we create new systems to understand the world. Is AI at the moment able to uniquely generate its own sign systems, or is it completely reliant on the sign systems that we give it? And if it's not capable of it, do you think that it will eventually be able of doing something like that?
Yes, it is. It is capable, and depends upon the goal it gives it. You give it. For example, there were many experiments where you have two machines communicating, and you gave them the goal to communicate, but using a smaller vocabulary or faster communication or cheaper in terms of energy. And they were able to do that. There were many experiments done, and it's feasible. Now, we have, as you said, we have different systems, and different cultures create different systems. And each system has limitations and its advantages. You can express something in one language and not really expressing the same thing in another language and so forth, because the different cultures had different goals. And that's how languages evolved. And they copy from each other, and they invent their own stuff. Computers are able to do that. We are not doing it. There was a media coverage recently, well, about 2 to 3 years ago, when one big company doing this, I'm not naming the companies, but they did that. They reached their goal, and then they turn off the experiment, and the media was saying, oh, computers were able to communicate in a language that humans cannot understand, and that's why they turned it off. Has nothing to do with that. So computers are able to create ways of communication that is either more efficient or faster or whatever you give it as a target to maximize. But there's no purpose for it right now.
I guess I have a follow-up then, if that's okay. So if AI is able to understand science systems at the moment, doesn't that mean that them being able to write their own code is around the corner, since they would have to have
yeah. So that is getting there. Still very simple kind of programs they can do. They can also generate language in English, like you and I are talking. We create what we call a language model from a large corpus of text, and they are able to generate grammatically, perfectly, syntactically correct sentences in English, and it seems to the point and everything, but it doesn't mean that they understand. They don't understand what they generated. I mean, I have a team working on response generation and trying to keep it not just on topic, but also keep it grounded on some knowledge. And it's not easy. Computers hallucinate because they're basing it on the language model that they learn, and they talk about something else. We call it hallucination. So we're still in the beginning of this. We will eventually do that. And they will be able to program. I don't know how long it'll take before they start programming like we do, but the day computers are able to program like we do, things will go way faster. You remember I said we are improving hardware, but software was still far away. Maybe then software will catch up.
Thank you.
Okay, well, it's been a great teaching session. Thank you very much, and we look forward to Thursday. So,
Thank you.
great, thanks.
Bye, guys.
Bye-bye.